Hello, my friends. Welcome to Unit 8, where, would you believe it, I'm finally out of ideas. I don't know how I'm going to start the video, Mommy. Any suggestions for me?
Honey, you've already started it.
This is objectively true. I've got something even better than an intro for all of us today. Mama Volel is here with us in the studio once again. Say hi, Mama Volel.
Hi, friends.
Yay, she's been released from her prison in the basement, and she's here to help teach us about graphing quadratic equations. So,
Yay.
We closed out Unit 7 by seeing how factoring could help us solve a bunch of polynomial equations, and among them, the type of equation we most often worked with, we called quadratics. Mommy, do you happen to remember what makes a quadratic equation quadratic?
I think it has to do with squaring.
Yeah, so quadratic, four sides, exponent of 2 is called a square. A quadratic equation, right, we were working with polynomials. This is a specific type of polynomial where our highest exponent that we will see is 2. The way that we word that, of course, is that we say that the degree of our equation is 2. Very nice. But we also saw that there were lots of prime quadratics in Unit 7 that we didn't know how to factor, which means if we want to be able to solve any quadratic equation, there has to be more than just factoring to help us solve. And as it turns out, there are 2 methods awaiting us in Unit 9. And we will learn about them soon enough. But first, seeing what we're actually doing when working with quadratics will hopefully give us some helpful insight into how those strategies work. So with that in mind, if we want to visualize, we've got to talk about graphing. Now, an important thing to remember when we're graphing an equation we often forget actually tells us something about our equation. Mommy, do you remember if I'm graphing an equation, what does that really visualize for me?
The points XY relationship.
Good, so it gives me all of the points x and y that when I plug back into the equation makes the equation
true.
True, which means the things that make it true, that's the set of solutions. So, oh, look at that. You've got a dog barking in the background. How fun. Please ignore him. He's annoying. The graph of an equation we often forget. Listen, he's my son too. I can talk about him however I want. He is. Okay, so our solution set, right? It's the set of all points that make our equation true, the collection of all of those solutions. Very nice. So since it's been a minute, to help orient us, we eventually want to graph quadratics. Let's remember where we came from and graph a line. So say, for example, I want to graph y equals 2x minus 3. You'll hopefully notice, the eagle-eyed among you, that this is an equation of particular form. Mommy, do you happen to remember, what's the special name that we give a linear equation like this where y is by itself?
I do not.
So this is called our slope-intercept form.
Yes,
so when y is isolated, right, the coefficient of x and then this constant term off to the side, they serve a special purpose on the graph of our line. Do you happen to remember what this 2 or this negative 3 are? Either one?
2 is the slope.
Good.
And 3 is the intercept.
Yeah, which intercept?
X.
Other one.
Y.
Yeah, I'm on the y-axis. Good. So my slope and y-intercept here are hiding in plain sight. So we could use that to graph by plotting our y-intercept using our slope to find points. But before we knew how to use slope-intercept form, there was another method that I believe it was you who actually helped introduce us to. How else could I graph this line if I didn't know slope-intercept form?
We had a 3-column chart.
Yeah.
And we would take values of x and figure out the y.
Very good. So let's give ourselves a little chart here. I want to find some values of x and y. At home, take a minute, pause the video. Remember, we want at least how many points on the graph of a line?
I'd say 5. 3, 5.
3, yeah. We can make any with 2, but 3 gives us a fail-safe to check. At home, pause the video, take a minute. See if you can find me 3 points on the line. Let's dust off those cobwebs. Go! All right, Mommy, let's do it. So, if I'm thinking strategically, what's the easiest thing for me to do here?
X equals 0.
Yeah, let's start by plugging in x equals 0. So y is going to be equal to 2 times 0 minus 3. Now I can solve for y.
Y is going to be 0 minus 3, therefore minus 3.
Very good. So if x is 0, y is negative 3, right? What does that tell me? What's the point on my graph?
My x will be at 0.
Good.
And my y will be at minus 3.
Very nice. So here's our y-intercept at negative 3, right? You'll notice here, as we wrote in our slope-intercept form above, that matches the y-intercept we identified. Cool. What's the next easiest move for me to make here? I want to find at least 2 more points.
1. X
1?
equal to 1.
Sure, let's do it. So we can plug in 1 for x. You could plug in 0 for y. You could do a bunch of things. Let's make 1 equal to x. So y is going to be equal to 2 times 1 minus 3. 2 times 1 is?
2.
2. And 2 minus 3 is?
Minus 1.
Negative 1. So that tells me that the point 1 comma negative 1 is on my graph. That guy would be right over here. I'm being really good, so I'll label my points. Last one?
X equal to 2.
Sure, let's make x equal to 2. So here y is going to be equal to 2 times 2 minus 3. 2 times 2 is
4.
4. 4 minus 3 is
1.
good. So y is going to be equal to 1. X is going to be equal to 2. That tells me that the point 2, 1 is on my graph. And that guy, of course, lives right up here in our first quadrant. Cool. A couple of things now that I need to do to complete my graph. First, really egregious choice that I probably want to make.
I want to make my line.
Yeah. So
Showing
it's not...
infinity.
Yeah, right. So I'm going to go all the way off. Very good, right? Indicate infinitely long with some arrowheads. Some other things that I might want to do for full credit.
Label my x and y axes and make them infinite as well.
You remember better than my students do. Let's draw our arrowheads, right? It's a number line. It keeps going. Let's indicate which one is x and which one is y. Cool. So now that we know how to graph a line, we want to figure out how to graph a quadratic equation that also shows up in two variables, x and y. And the thing is, we'll often find them, just like we were interested in doing all of that work in standard form in Unit 7, we'll find them in standard form as well. Mommy, what makes this equation y equals ax squared plus bx plus c in standard form? So standard form has to do with the exponents.
Exponent, yeah.
So here, notice the x squared is at the front on the right side. Yes. X to the invisible power of 1 comes second, and then there's no x here attached to c, really x to the invisible power of 0. So I'm ordered in decreasing power order, biggest exponents at the front. The only difference here is that now there's a y equals on the left side. Let's think. If I want a quadratic equation, which means that my exponent has to be 2, what's the simplest possible quadratic equation that I think I could have? Take 5 seconds, take a guess, pause, go. 4, 3, 2, 1. Mama?
Y is equal to x squared?
Yeah, so the simplest thing that I could possibly have to meet my criteria here just needs to be quadratic. So there needs to be an x squared. We'll say it has an invisible coefficient of 1, no linear term, no constant term. Cool. Same idea as before. I want to see what the graph of this looks like. If it ain't broke, don't fix it. Let's make a table. So I'm going to give myself some values of x, and I'm going to plug in to find some values of y. Probably the easiest value of x to start by plugging in with would be
0.
Yeah, let's start with 0. So here, x is going to be equal to 0. So y would just be equal to 0 squared, which means y is
0.
0. So that means x is 0, y is 0. The point 0, 0, where does it live on my graph?
At the intersection of x and y axes.
Good. Do you happen to remember the fancy name that we give this point that lives at the intersection of the x-axis and the y-axis?
Origin?
Yeah, it's the origin. It's where we start. It's where our axes originate from. Good. Let's find some more points on this graph, flesh it out a little bit. After 0, what's the next nicest number to plug in for x?
1.
Probably 1. So let's take 1 here. Y is going to be equal to x squared, which is just 1 squared. 1 squared is?
1.
1, right? 1 squared means 1 times 1. So my point here is going to be at x is 1, y is 1. That guy is right there. After this, give me another point.
2.
Yeah, let's try 2 for x. So here, when I plug in 2, y is going to be equal to 2 squared. 2 squared is?
4.
Good. 2 times 2 is equal to 4. So the point 2, 4 is on our graph. Now the eagle-eyed among you might notice this is already starting to look a little bit different from the graph of a line. Let's go to the left of the origin and see what happens just for fun. Give me a nice small negative number to plug in.
-1.
Let's try -1. So when I plug in -1, y is equal to the square of -1. What's -1 times -1?
1.
+1. So interesting. Now I take my negative and it flips the sign to a positive. That's a little bit wonky. Let's try it with -2. Y is going to be equal to -2 squared. -2 squared is?
4.
+4, right? -2 times -2. That point is going to be right up here. Now I could imagine I could keep going here. I'll cap out at 5 points, but just like before, I'm going to connect these points with some kind of line. And in fact, that line is not going to be straight anymore. You'll notice, right, I start over here by going like a little bit up, but then the amount that I go up from my first point to my second point is relatively bigger. So I'm kind of like increasing a little bit in the amount that I'm going up here. Same thing on the other side. When I connect all of these points, I form an interesting shape, this graph of y equals x squared. Mommy, do you happen to know what the name of this shape is called?
I actually do. It's a parabola.
Very nice. So the graph of any quadratic equation we say is a parabola. P-A-R-A-B-O-L-A. If you want to know the etymology of this word, don't ask me, I don't know it. It's probably Greek. There are a couple of things that we want to say about this parabola. Take a second, pause the video, tell me at least one interesting thing that you notice about its shape. Be creative, take a risk, take a chance, who cares? Go! All right. Mama Volel, any observations, anything at all that strikes your interest?
The first thing I notice is that it looks symmetrical. There's a mirror image across the y-axis.
So maybe my squiggly wonky line hasn't done the best job of conveying it, but if I look at the y-axis, on either side of the y-axis, there is some symmetry to our graph, right? It's the same picture. It's kind of like a perfect reflection. This line here, it happens to be the y-axis, but it won't always be. We call this line for our parabola its axis of symmetry, right? It's here going up and down. So what kind of line is it?
Vertical.
Good. So it's a vertical line here that's cutting our graph perfectly in half, forming a mirror image, creating that symmetry. Interesting. Any other observations for me?
I do notice that it's diverging away from that line axis of symmetry. So both ends are increasing away from the distance.
Yeah. So we'll take that and kind of do it in a slightly different way, but what you're saying is perfect. In math, just like in English, we read from left to right. So notice here, whereas for a line, our line always was positively sloped, always negatively sloped, here it's different when we're working with a parabola. When I'm going off to the right of that axis of symmetry, remember I like to think of it as taking my finger and tracing along the graph. Here, as I take my finger and trace along this graph, what's my finger doing? Is it going up? Is it going down? Is it staying the same?
It's going up.
It's going up. So I would say that this part of the graph, right, as I move left to right, my y values are going up. Another way to say it's going up is the y values are?
Increasing.
Increasing. So I would say this branch of my parabola is increasing, whereas on the other side, right, as I read from left to right, here my finger does what as I trace along it, Mommy?
Decreasing.
Yeah, my finger goes down. So I would say that branch over there is decreasing. And there's one more important thing that I want us to observe about this parabola. Anything else that you notice?
I noticed that at the bottom, close to on the x-axis, we're actually going from decreasing to increasing.
Good.
It's
so
like a turnaround.
Yeah, so there's like a little turnaround point here. Notice we did not have that when we were working with lines, right? We always kept going up or kept going down. Here there's a lowest point on our parabola. The fancy name that we give it, we call this the vertex of our parabola, which, as Mama Volel alluded to, we will describe or define in two equivalent different ways. Nice. Let's write some of these observations down. So given a parabola, there are a couple of things that I might want to say about it. We'll call them the characteristics of a parabola. The first we've talked about increasing and decreasing. I again like to think of it as taking my finger, tracing along. If you want a more mathematical description, my graph increases when my y values go up as I move from left to right, and decreases when my values of y go down from left to right. My vertex, it's such an important point. I can speak words, that's why I teach math. So important on the graph of our parabola, we give it a fancy pair of values. We call it the point h comma k. So h specifically is its x value, k is specifically its y value. And as we've alluded to, there are two equivalent definitions for the vertex. The first one that we'll say, in the parabola above, our vertex was at the bottom, right? So we called it the lowest point. But sometimes the parabola, right, it might be flipped over. So it can also be at the top of the parabola. In other words, it's the highest point of our parabola. If I want to be a little bit more mathematical with it, another way to say I'm at my lowest.
Minimum?
Yeah, right, I'm at my minimum value. And if I'm at my highest?
Maximum.
Yeah, so I can also call this the maximum. So sometimes we say that it's the minimum of our parabola. If it's at the top, we say it's the maximum of our parabola. But then, as Mama Volel also so wisely, sagely noticed, the vertex is also where we flip from going up to going down, increasing to decreasing. So we'll write that as well. We say that our interchangeable definition, this can also be the point where our parabola will say, quote unquote, flips, not strictly mathematical, but who cares? It flips from increasing to decreasing, or vice versa. Cool. We also have this axis of symmetry. Again, for our parabola, you notice what kind of line was it, Mommy?
Straight and
Straight,
vertical.
going up and down, right? So it's vertical. So the axis of symmetry is a vertical line. And in fact, it always passes through the parabola. or not the parabola, through the vertex. Thank you, good correction. So this passes through our vertex, and because it passes through the vertex, that means that it's always going to have a specific equation relative to that vertex. So first of all, for a vertical line, this is a real throwback. Mommy, do you happen to remember vertical lines? Their equations are always either x equals or y equals. Do you remember which one is a vertical line?
Vertical x equals.
Yeah, vertical is x equals. And it's a little bit counterintuitive because usually if we're thinking up and down, we're thinking y values. But if x is equal to something, that means x stays the same. It does not differ. So I'm not going left or right, but I am going up and down, right? I'm vertical. So here, if the vertex is the point h comma k, and the axis of symmetry passes through the vertex, what's that x value going to need to be?
Using those, it's
yeah, my vertex is, yeah, right. If the vertex has an x value of h and the axis of symmetry passes through that vertex, its equation would be x equals h. Very nice. The last piece of terminology we'll introduce describes the shape of our parabola. We have concave up and concave down. We talk about the so-called concavity of our graph. Mommy, what does a concave up parabola look like?
Its vertex should be the bottom, so it's opening upwards.
Yeah, so I like to think of these as happy parabolas and sad parabolas. A concave up parabola is happy. The way that we describe it mathematically, we say that that parabola opens upward, right? So it has kind of like a dent. It's opening upward. It looks kind of like a smiley face. I like to think of it as. The other way that we can say that here, right? The vertex of the parabola, is it going to be at its lowest or at its highest, right?
Minimum.
We just indicated it's going to be the minimum value. And same thing for concave down, right? If our concave up is happy, our concave down gives us like a sad face parabola. So we say that our concave down parabola opens downward. Or equivalently, here the vertex, is it going to be a minimum or a maximum?
Maximum.
Very nice. So we say here that our vertex is a maximum. Very nice. Any questions here about our terminology, Miss Volel?
Nope, we're good.
Cool. 4 more pieces of terminology for you then. On the graph of a parabola, there are 4 other characteristics that we might identify. In fact, this would come for any graph. It's not just for parabolas. The first one, domain, often indicated with a capital D, is the first characteristic that we'll talk about here. We'll talk about it again in Unit 10 in a slightly different context when we introduce functions. So domain is just talking about specifically something that's true about my graph. What am I talking about, Mommy, if I'm indicating the domain of a graph?
Domain is the set of all the x values.
Good. Domain, and I would not expect you to know this if you didn't have any prior knowledge, it is just a fancy way for me to say, what are all of the x values that I can have on my graph? By the same logic here, its twin is the range. If domain gives me x values, what would the range tell me?
My y values.
Yeah, so the range is just what are the possible y values that I can find on my graph? The x-intercept and y-intercept, we've found those before. That should be familiar. What am I asking for, Mommy, if I'm asking for the x-intercept or x-intercepts?
So x-intercept would be where the line or the parabola crosses the x-axis.
Very good. And if I'm looking algebraically, what would happen if I'm crossing the x-axis? Like, what's unique about all points on the x-axis?
Y 0.
Good, right? So if I'm looking for the x-intercept or intercepts, the way that I find it is by plugging in 0 for y. And I could do the same thing for the y-intercept. If I'm on the y-axis, how would I find my y-intercept?
Then I would plug in 0 for the x value.
Very good. So this is going to be the value of y when x equals 0. There you go. Lots of terminology for you. Now that we've got it, let's get a little bit of practice using it. Let's do this one together, and then I'll set you loose on the next and last one. Here's our original parabola, our graph. By the way, I forgot to mention, and I should have, because this is our simplest possible parabola, it's the one that all others come from, mathematicians sometimes call this our quote-unquote parent graph, right? All of our other possible graphs that we would find are like children of this. They all look the same. So, for this graph, let's indicate some characteristics. We can go for any of these, but using those definitions above, we just want to describe what's our domain range, where is our vertex, is it a maximum or a minimum, are we increasing, decreasing, whatever. So, Mama Volel, help me out. Where would you like to start with this graph?
Start from the top.
Okay, so let's start with our domain. So this is asking me, what x values can I plug in to y equals x squared?
Okay, so we're going infinitely away from the y, so we should have minus infinity to infinity.
Nice. So the thing about domain and range increasing and decreasing, here is where all of that work we've done with set builder and interval notation comes back to bite us in the butt. So my domain is saying x values that I can have. If I think about this logically, is there any number that I don't know how to take the square of? Like if I'm thinking real numbers, 1, -1, square root of 3, 0.5, is there any number that I can't multiply by itself?
No.
No. So that means anything can work. I can plug anything in for x, which we indicated as the set of all real numbers. There's no number that I don't know how to square. I can also indicate this, Mommy, you alluded to the interval notation, right? If I'm real numbers, I'm going all the way off to the left to
Minus infinity.
negative infinity, and all the way off to the right.
Positive infinity.
Very nice. So you can choose either of these, whichever you prefer. If you like set builder, use set builder. If you like interval, use interval.
Quick question.
Yes.
I say minus, you say negative.
Yeah.
Is there one that's better than the other?
Nope, just semantics.
Okay,
Cool.
good.
I mean, you could use minus to refer to like the,
Subtraction?
yeah, like the operation, whereas negative would talk about the quality of the number. But hey, who cares?
Got it.
All semantics. Last thing I need for interval notation, though, parentheses or square brackets. So square brackets indicate that a value is in the solution set, whereas parentheses indicate that it is not. Negative infinity, infinity, do they get brackets or parentheses?
Parentheses, because it's
Good.
not truly a number.
Yeah, they're concepts, right? I can't actually plug them in, so both of these get parentheses. Very nice. Now our domain is everything, but our range is different. Looking at my graph here, Mommy, how am I restricted in y values? What y values can't I have here?
No negative.
Good.
integers.
Looking at my graph here, notice I don't go below the x-axis. So there are no negative y values here. How could I indicate that in either set builder or interval notation? I can't have negative numbers.
So I would have to have 0 to positive infinity.
Good. So if I can't have negatives, right, I would bottom out at 0. Would that 0 here get a closed square bracket or an open parentheses?
No, because that's the vertex.
Yeah, but is this point 0, 0 on the graph?
Yes.
Yes, so 0 is an output value.
okay.
It gets a square bracket. Good. So
Oh, I
here's
thought
my
you said
interval.
Parenthesis. I'm sorry.
Nope.
Got it.
That's
Got it.
okay. She needs to get her ears checked. She's getting old.
An
Anyway,
appointment for Monday. That's okay.
so here's my range, right? If I wanted to indicate that in set builder notation, so I could say range is, again, y values or x values.
Range is y values.
Good. So I'd say the set indicated by squiggly bracket of all y values such that here y has to be, can it be equal to 0?
Yes.
Yes. And then can it be greater than or less than?
Yep.
Good. So it's greater than or equal to
0.
0. Very nice. Vertex. Where is this point here that's at my bottom or my top?
0, 0.
Good. So I'm at the point 0, 0. By the way, that point 0, 0 is also doing some double duty here. What is it also acting like on my graph?
My x and y intercept.
Good, right? Notice here, this is where I cross both the x-axis and the y-axis. So we can jump around here. We don't have to do it in any particular order. Let's talk about the axis of symmetry. Now, the axis of symmetry, again, is what kind of line? Vertical or horizontal?
It's a vertical.
It's a vertical line that passes through the vertex. So it's going to be x equals or y equals?
Y equals.
Other
X
one.
equals, sorry.
X
Sorry,
equals.
X equals.
So if it passes through the vertex, it needs to have the same x-coordinate as the x of the vertex. So it's going to be x equals?
0.
Good. So the axis of symmetry here is x equals 0. Is this vertex the maximum or minimum value of my graph?
Minimum.
Good, it's at the bottom. And is my graph happy face or sad face? Opening up, opening down?
Concave up.
Good, it's concave up. Last thing I need to talk about here is increasing and decreasing. And increasing and decreasing is a little wonky. You might remember the way that we talked about it above is we said, well, what side of the axis of symmetry are we on? Increasing and decreasing, weirdly, are defined by x values. So, looking at my graph here, to the right of my graph, or the right of my axis of symmetry, is my graph increasing or decreasing?
Increasing.
Good, right? If I take my finger and trace along it, you could imagine my finger is going up. So I need to be to the right of this axis of symmetry, x equals 0. How would I indicate I'm to the right of x equals 0?
0 to positive infinity.
Good, right? So if I wanted to use my interval notation, I'm strictly off to the right of 0, so from 0 to infinity. Or I could say I'm increasing when my values of x are greater than or less than 0.
Greater than.
Good, so I'm greater than 0 here when I'm increasing. Decreasing would be off to the left of 0. So to the left of would indicate that I am
Than 0.
less than, or if I prefer my interval notation, right, I start at 0 on the right and I go off to
Minus infinity.
negative infinity. Very good. Now, the last question that you might have is, well, why do increasing and decreasing not get greater than or equal to, less than or equal to? Well, at the vertex, we define that as where we flip from increasing to decreasing. So at the vertex, I'm neither increasing nor decreasing. I'm switching, which is why we use our open parentheses rather than those closed brackets. Very nice. One last one for the road. Same idea here using those definitions and what we've just done above. Can you flesh out my list of characteristics for this parabola for me? Take a minute, try it out, have fun, but not too much fun. Go ahead. All right, Mama Volel, let's do it.
Okay.
Hit me.
Domain.
But not physically. I will call Child Protective Services on you. Okay.
Okay, so domain is the set of x, so it would have to be x is equal to minus infinity to positive infinity.
Good, right? Otherwise called the set of all real numbers. Again, at home, you're picking one of these notations, either interval or set builder, whichever makes you happy. By the way, this is true for every parabola. The domain will always be all real numbers. There's nothing here that I can't square and then multiply by -2 and then add 2, right? I can do that for any real number that I know. Cool. Range here. Where's my y value restricted?
So my y value is 2.
Yeah, so
maximum.
I cap out at 2. Good. How would I indicate that my y values max out at 2?
Y is equal to minus infinity to 2.
Good. So I can go all the way down to negative infinity, but it caps at 2. Would this 2 get an open parentheses or a square bracket?
I would say square bracket.
Yeah, it's included, so it caps out at 2. The way that I would write that in set builder notation, right? It's the set of all y values such that y must be greater than or less than?
Greater than, less than or equal to 2.
Yeah, right, less than or equal to 2. Very good. Where's my vertex here?
Vertex is at 0, 2.
Cool. Is that vertex a minimum or a maximum?
Maximum.
Good. It's at the top of the parabola. Is it concave up or concave down?
Concave down.
Cool. So here's an example where our parabola is opening downwards. I accidentally erased this because we did another take before this that I didn't like because Mama Volel was funnier than me. I need to know where my axis of symmetry is. Where is my axis of symmetry here, Mama Volel?
Axis of symmetry again is x equals
Good.
0.
Right, so it's always x equals. It's always the x-coordinate of the vertex. So if my vertex is at 0, 2, my axis of symmetry is that vertical line here passing through the y-axis. Good. Increasing and decreasing. So here, am I increasing to the left or to the right of that axis of symmetry?
Increasing to the left.
Good. So my finger goes up as I trace along to the left of the axis of symmetry. So how would I indicate that here? I need to be to the left of x equals 0.
So that means y is equal to...
So increasing and decreasing are defined by x values. Because we're saying to the left of x or to the right of x equals 0. So increasing...
minus infinity to infinity.
Good. So I'm increasing to the left of x equals 0. So it would be all the way off to the left of negative infinity. And then I cap off at 0. Good. That's okay.
Sorry.
It's tough. It's new. It's weird. So I'm increasing here. The way that I would write that in set builder notation, I want all values of x where x is less than 0 if I am off to the left. Or if I'm to the right, I'm decreasing. So the way that I would indicate that, yeah, so here I would say the set of all x values that are greater than 0 at my axis of symmetry. Or in interval notation, start off at 0, go all the way off at the right, good to positive infinity. Last but not least, let's find some x and y intercepts. So x-intercepts.
X-intercept is 0.
Yeah, so
I'm
where
sorry,
do I
there are
cross?
2 of them.
Yeah, where do I cross the x-axis?
-1 and 1.
Good. So this is where I've drawn in that like invisible, or not invisible, but in parentheses, that s, right? There can be multiple places where we cross the x-axis. In this case, this parabola crosses it at both the points, -1, 0 and 1, 0, but only one y-intercept at
0, 2.
Very good. Alrighty, we'll do some more practice with this when we see each other in class next time, but for now, you're free. Any parting words, Mama Volel?
Can I sing?
I'm scared.
You are my sunshine, my only sunshine. You make me happy when skies are blue.
Skies are gray.
Oh, gray.
Listen, I still get the last laugh. Alrighty, thank you, my dears, for hanging out with us. I will see you when I see you. Goodbye.